welcome to this third tutorial in the mini-series on calculus at the higher level. Now, the first tutorial was sort of a motivation about what the sort of fundamental role of calculus is in mathematics and science, namely essentially relating changes of inputs to changes of outputs. And then the second tutorial was more formal and essentially took that concept in the context of graphs of functions, and we could see graphically what it would mean to relate a change of an input to a function to the change of an output of a function. And the fundamental sort of equation of calculus that I've been writing is that a change in the output of a function f of x is related to the change in the input to that function, delta x, and the factor that relates these two things we call the derivative of f. And furthermore, in the second tutorial, graphically, we could see that if we considered a point x and a neighbouring point x plus delta x, then this change in the function naturally could be written as the function evaluated at the neighbouring point to x, take away the function evaluated at x. And this gave us then an insight into how we might actually calculate a derivative for a given function. And just as a reminder, all of this discussion is for delta x small. And I'm not using the formal precise language of calculus in this series of lectures at the higher level. It's probably would be overkill, to be honest. The real nitty-gritty of setting up the calculus involves what are called limits and infinitesimals, which are beautiful and quite important, but they do tend to obscure the basic ideas when you first see calculus. So what we're going to do here is essentially see how calculus works at a less rigorous level of mathematics, but still actually fairly formal. Get a lot of confidence with that, understand the geography of calculus, and then at the advanced higher level, it's quite straightforward then to go back and just, sort of sew up those seams with a tighter stitch, as it were, using the more formal language of infinitesimals and limits. But I don't want to do that here because I don't think it's going to be tremendously helpful for students at this level. Now, the last lecture was a difficult one and quite abstract. So what's really important now for the next few lectures is to look at some specific examples of functions and to essentially apply the calculus with our bare hands and actually derive this f primed, this derivative. There is a tendency, I think, perhaps more nowadays, to teach calculus in high schools as a set of formulas without actually deriving them. And I think it really leaves the students rather nonplussed because they perhaps don't really understand what on earth's going on. It's really just, they just see that there are some rules they have to memorize. So there'll be no rules to memorize here. We're going to derive everything, and I think you'll find it very satisfactory. So what we're going to look at in this third tutorial is deriving the derivative for a parabola. And people who've looked at these tutorials for a while will know that I do have a certain penchant for parabolas. That is true. They're very beautiful functions. So we're going to ask, if we write down a function f of x as the simplest parabola, namely x squared, can we use this machinery here that we've set up to derive the form of the derivative? And once we've done that, what we'll actually do is look at two simpler examples, a straight line and a constant, a function that is a constant. But I'm not going to start with those really simple examples because they're so simple I don't think you get much out of them in terms of insight. So I think x squared is a really good place to start. So let's do that. And just to mention, in the next tutorial, I'll be looking at a generalization. I'll be looking at x to a power of n, where n is any positive integer. Right, here we go. So let's look at f of x equals x squared. So here we are, our xy axes, and let's see if we can draw a nice parabola here. Not too bad. That will do for our purposes. Remember, this is a symmetric function about the y-axis. One might say it's an even function. We learned that term in one of the earlier tutorials on functions. Now, you'll remember two things that I really stressed in the previous tutorial about this f primed, which we call the derivative. Just to remind you of this terminology. The derivative. One thing that we learned is that if we're looking at a particular value of x, the derivative ultimately is the slope of the tangent to the curve at that point x. The second thing that we learned is that generally, because the slope of that tangent to the curve will change as we vary x, then f primed is itself a function. So what I'm going to suggest we do is to think about, well, what would that function f primed look like as a function of x for this example? And we're not going to try and plot it, we're just going to get a feeling for it. Okay. So I'm going to be plotting here y equals the derivative, which we don't know anything about right now, but we're going to just get a feeling for it. Now, we can already, without going into any sophisticated mathematics, start to see what's going on here. Let me use a different coloured pen. This derivative, this beautiful creature which is going to open up a whole world for us, just, with a few lectures time, have tremendous power to do all sorts of things in maths and science. This derivative is sort of like a translator. It takes it translates from a change in an input to a change in an output. So let's imagine doing a little sketch here of looking at, say over here, let's look at what a change in the input would actually sort of look like. And I'm going to try and use the same sort of size of change of input. So that's my tiny little arrow there, is my sort of change in input delta x. And you see here the change in the output is fairly big. That's my change in the output over there. Sorry, that's so tiny. I hope you can see that. Let's do it a bit closer in to the origin. So here then, I've got the same size change of input. And let's see what sort of size of change of output we're going to have. You can see it's really tiny. So by going closer to the origin for this function, the change in the output for the same size of change of input has gone from something quite large to something really very small. And if we were to go all the way down here into the origin, if I looked at the change of output for a change of input in this range right around the origin, I can't even draw it, it's tiny. The function barely changes there. So on this graph in quotation marks, because this is really more of a kind of a thought graph, a Gedanken graph here. We're not going to plot a function, we're just going to say, well, for x out here, a change in the input gives quite a large change in the output, so the derivative must be kind of fairly big. So we're going to get some fairly big value there. But as I go in closer to the origin, change in the input here gave a much smaller change in the output. So we're going to, here, around x around this value, the change in the output is much smaller. And this derivative is the translator from a constant change in x to these different changes in the output. So the translator f primed has to be a lot smaller here. And then near the origin, actually, look, it's barely measurable, so it has to be sort of very, very, very small. So whatever this function f primed looks like associated with f equals x squared, it somehow has to go through these kind of clouds that I've drawn. And we know that this is a symmetric function, so there has to be some kind of symmetry going on here with the translation as well. So let's look on the negative side. Let's look, say, at this fairly large value of x. Now, the negative one, so the same magnitude but negative. Okay, so there's my change in x. And I want to be quite careful that I draw roughly the same size. Let's just take that parabola a bit higher there. And we have that equivalent, I haven't drawn this perfectly symmetrically, but we have that equivalent change in f there. What you'll see though is that we define the change in f as the right point take away the left. So we had a positive value for delta f here. Delta f here will be negative because the right point is less than the left point. So it's going to have the same size as this one by symmetry, but it's going to be over here. So for x values which are in this range but negative, we expect that this f primed will sort of be over here. Now, you know, we can sort of see, well, that looks like a function we've seen before. We're not going to say what that function is, we're going to derive it, but it's worth going through this exercise to get a feeling for what a derivative is. You know, at the risk of being very tiresome here, and I do apologize, but I keep trying to stress in these tutorials that maths is not about memorizing formulas and such. It's really a set of connected ideas, and there's so little memorization involved if you're able to draw on, you know, intuition and experience from earlier parts of maths. So what we've done here is really just sort of used some experience of sketching functions and thinking about slopes and so on to kind of intuit, well, what will f primed kind of look like for this particular function? And in fact, the reason this is very useful is that if you get some much more complicated function, as long as you know the shape, you'll be able to draw these little clouds or bubbles, you know, and that will give you a very good first sort of sense of the shape of the function, the derivative. And, you know, that will be then a good kind of guide once you've derived the derivative to make sure that you haven't made any silly algebraic mistakes, because this, in a way, is far more reliable than the mechanics of algebra. But speaking of algebra, we're now going to derive this. And let me do this in a different color. I think I'll choose red. So we would like to calculate delta f. All right. Where f is x squared. And it's the function evaluated at this neighboring point x plus delta x. We have to remember our f of apple stuff here from the functions tutorials, not to get confused about arguments of functions. So this is f of apple, where apple is x plus delta x, and the function is f of apple is apple squared. So we simply have x plus delta x all squared. And then we take from that just f of x, which is x squared. Okay, that's straightforward. Well, let's just multiply this out. This is just algebra here. So we have x squared. We have two lots of x delta x. And then we have delta x all squared. And then we have negative. Then we have take away x squared. So the first and last terms cancel. And we're left with 2x times delta x plus delta x all squared. Now, the key point now is that we want to think of this delta x small, and in fact what we want to do is think of it so small that we actually take it to 0. And this arrow is often a symbol for goes to 0. So we want to take delta x as small as we like, ultimately approaching 0. And you see if we do that, that this term, because it's delta x squared, as delta x gets smaller and smaller, this term becomes much, much, much smaller than this term. Just to give you a sense of that, let's say delta x was 1,000th. Then this would be like 1,000th squared, which is 1,000,000th, and this would still be of order 1,000th. So as you make delta x smaller and smaller and smaller, this term becomes vanishingly small compared to this term. So as delta x goes to 0, then this delta f, essentially, I'm going to just write it like with an arrow, goes to 2x delta x. And if we compare this with essentially our definition of the derivative, we can read off the derivative here. Namely, it's this thing multiplying delta x. So we have that f primed of x is equal to 2x. And that has completed the first of a number of derivations we're going to do of derivatives. And we haven't had to rely on someone telling us this. We've actually derived it with our bare hands using some pretty simple algebra, that the function f equals x squared has a derivative equal to 2x. And look, that's completely reasonable because our clouds here map out essentially a straight line. What we don't really have a good sense of at all is the slope of that line, but we do know it's something like a straight line. So when we've gone through this derivation and found indeed f primed is a straight line with a slope 2, that passes the plausibility test that we have here from intuiting from the function. Now I just want to take one little step back here because this is actually fairly important. There's a slightly neater way of thinking about deriving this derivative, which is very, very similar to this, and I just want to show you that. And we did, I think, write this down at the end of the last tutorial. Thinking of delta f as this difference in the function at the kind of right neighboring point, take away the function at x, and looking at this relationship, we can see that f primed can be derived from taking delta f divided by delta x, and I want to write delta f like that, as f of x plus delta x, take away f of x, all divided by delta x. Okay, so I've essentially written f primed as delta f divided by delta x, and I've written delta f in this form here. And then I'm just going to put a line here and say for delta x very small, and I'm actually going to say delta x goes to 0. And this starts to look more like the formal definition of derivatives when you go through this, slightly more advanced set of ideas regarding limits and infinitesimals. But we can see exactly where this comes from the discussion that we've had so far. So this is quite a nice way to think about it, because when we got to this step here, you see, for our particular function, we could have written that f primed was 2x delta x plus delta x all squared divided by delta x, and we want to take delta x to 0, and you see we then have 2x. We cancel one factor of delta x, so we have 2x plus delta x, and we want to take delta x to 0. And then you can see we don't have to sort of make this argument about, well, this is very, very small compared to this, because now we have that f primed is something which is absolutely non-zero as delta x goes to 0, plus delta x, which we're just going to take to 0. So this becomes 2x. Very, very clean. So this is a cleaner way to get to exactly the same result. We're just doing exactly the same calculation, but we're dividing by delta x from the outset and then taking delta x to 0, and it's a very clean way to do that. So I'm really pleased to have provided to you a derivation of the first derivative for a given function and of a number that we're going to do, and I hope you found that actually relatively straightforward. Now what I'd like to do on this little bit of territory that I have left, if there's room, is just quickly look at two simpler functions and just show you what the answer is going to be. So let me, I think, carve out a little bit of space here just so that I can have as much space as I can, sort of get my elbows out a bit without actually making things really confusing. Right, okay. Okay, good. Let's actually take a simpler function. Let's take a straight line. So let's look at the function f equals a gradient times x plus a constant. That's our old friend from National 5 Maths, y equals mx plus c, the equation of a straight line. And let me just draw some straight line here. There it is. That's the function now that we're looking at. And I think you can see here quite straightforwardly that as I change x and I look at the change of the output of the function for a given change in the input, that change in the output does not care whereabouts I am in x. The change in the output will always have the same size because it's a straight line. In other words, the tangent to this curve for any x is the curve itself. And so the slope of that tangent is always m. Therefore, for this straight line, the derivative, which is the slope of the tangent to the curve, is a constant, is always m. So we would expect for this straight line that if I draw a graph of f primed, the derivative for this function against x, that we should just get a constant value, which would actually have a size m, the slope. And let's just very, very quickly show that. I've got almost no space left, but really I don't need too much space to derive this because it's very straightforward. So I want to basically, let's use this formula here. F primed is going to be the function evaluated at x plus delta x. So that's going to be m times x plus delta x plus c. Take away the function evaluated at x. So take away, and then in brackets, mx plus c. And you see that a lot of these terms then cancel. So m times x cancels with that m times x. C cancels with c, and I only have one term left. Oh, silly me, I forgot to divide by delta x, which is very silly. Okay, let me do that. Only one term survives on the top, which is m delta x, and then we're dividing by delta x, and you see even without taking the limit delta x goes to 0, we just get that constant m. Okay, so that's the second derivative that we've found, a really easy one, that for a straight line, y equals mx plus c, regardless of this additive constant, the derivative of this straight line is just the slope of the straight line, is just m. Good, okay. Maybe just one last thing to say then about this, this example of the straight line is that if we had taken y equal, or let me call it f of x equal to x, in other words, if we had taken this straight line with m equals 1 and c 0, then we would find that the derivative f primed of x equals m equals 1. So these two examples, the derivative of x squared being 2x and the derivative of x being 1 give us a seed of an idea what the general case might be if we have f of x equals x to a power, where that power is a positive integer. Maybe we can intuit what the form of the derivative is. And in the next tutorial, we're going to derive that, and it won't be actually very, very difficult. So I hope you've enjoyed this. I find this quite pretty. I mean, I've done this for many decades and so on, but I don't know, I just enjoy doing this. It's just nice to do calculus with your hands rather than just being given tables of formulas to memorize. I've used this metaphor before of a potter dealing with clay. I think that's how you should think of maths when you're a budding mathematician or scientist. It's just to take this stuff and use it as clay would be to a potter, that you can't break it, you can't break it so long as you don't divide by 0 and you don't pervert the nature of an equation that the left-hand side must be the right-hand side. So it's an unbreakable toy pretty much, and you can play and have great fun actually. So, good. I'll see you in the next tutorial where we're going to find what the derivative is for x to the n. See you then.